Well, it's a great pleasure to welcome you all back. I think a lot of you have probably been in this position with me lecturing to you before, but this will be perhaps a bit different. It's a particular pleasure to talk about the subject of symmetry. Symmetry is something that has been close to my heart for the whole of my life. It has been a central feature of my research for many decades. And I want to start in what may seem a rather unlikely place, namely Agra. You will probably know Agra as the site of the Taj Mahal, but it's also the site of this building, which is the sometimes called the Little Taj, the tomb of Itmad-ud-Dawla, who was the chief minister of Shah Jahan, the emperor, Mughal emperor. And it is particularly well known for its the geometric patterns. And the reason I'm putting it up here is that my father, who was a mathematician, made a study of the patterns on this. He was very interested in them. And this was really my first introduction to the idea of mathematical symmetry. This is a very interesting pattern, as I'll explain in a moment. What is a symmetry? A symmetry is something you can do to an object or an image that will leave it essentially looking the same. In geometry, the simplest examples are from tessellations. These are patterns of regular shapes, tilings, that can fill the whole of a plane with regular shapes. And you can very easily produce patterns like this that have a four-fold rotational symmetry, and ones like this that have a six-fold rotational symmetry. What you cannot do is to produce a five-fold rotational symmetry. You can start the process. You can draw a regular pentagon and surround it with a regular decagon and surround it with pentagons, but this pattern always goes wrong somewhere. And in fact, the pattern I showed you earlier is an example of precisely this phenomenon. You can see that these are actually regular decagons, essentially, and surrounded by 10 pentagons, but in between them they are squashed together. It's one of these beautiful mathematical theorems that says you cannot have a pattern, a repeating pattern, with a five-fold rotational symmetry. It's a very simple thing to prove. Of course, it's relevant to crystal structures, for instance. Now, symmetries are actually very often useful to us in solving problems in physics. Well, I'll come back to that in just a moment. I want to first of all say these were discrete symmetries, but in physics, we're more often interested in continuous symmetries, or at least in the kind of physics I've been doing. And continuous symmetries are related to conservation laws. This is a very famous theorem, Noether's theorem, proved by Emmy Noether in 1915. Continuous symmetries are typically associated with conservation laws. For example, translational symmetry. Translational symmetry means that you can move the system to somewhere else and it will behave exactly the same way. There's no preferred origin in space. And that implies momentum conservation. If you have a system where there's an external force, you have a system and then you have, say, the Earth as a separate thing outside the system, then you don't have momentum conservation. And the same is true between the translations in time. There's no preferred zero of time, and energy conservation. And between having no preferred direction and angular momentum. And this relationship extends beyond space-time symmetries it applies also to others. For example, if you make phase rotations of charged particle wave functions, this doesn't change anything physically, and that symmetry is related to the conservation of electric charge. I'll say a little bit more about that in a while. Now, as I said a minute ago, symmetries are useful. Suppose we have this nice circular bowl, and we have a marble, and we throw the marble into the bowl. If you try to follow the motion of it as it rolls around here, that's a very complicated dynamical problem to solve. You can do it, of course, but it's complicated. However, if you're only interested in where this comes to rest, once it's come to rest, symmetry will give you the answer. It has to be at the symmetric point, the lowest point of the bowl. Now, of course, this doesn't always work. It doesn't work with a roulette wheel for obvious reasons. The roulette wheel doesn't have the symmetry, actually, because there are 37 little indentations where the ball will end up. But even if there is a symmetry, it doesn't always work. For example, suppose we had a bowl that's shaped like the base of a wine bottle. Then, and you throw a marble into it, it's not going to end up sitting on the top of the hump in the middle. It's going to end up somewhere around this, the circle where the lowest point lies. And that is an example, what happened? Oh yes, that is an example of spontaneous symmetry breaking. It's spontaneous in the sense that you don't know a priori where in the base here it's going to end up. It could be anywhere. That choice is made randomly, spontaneously. And spontaneous symmetry breaking is a very widespread phenomenon in physics. It occurs at many phase transitions. Very often there's a high temperature phase in which the symmetry is clear, and a low temperature phase in which it is broken. The simplest example I know is crystallization. Let's have our circular bowl again, sit it on a table full of water. It looks exactly the same from every direction around. But when it freezes, the ice crystals will form in specific directions, and that breaks the symmetry. It means it doesn't have the full rotational symmetry anymore. This is spontaneous symmetry breaking in the sense that unless you know something else about the defects in the bowl or something like that, you don't know which direction the ice crystals will choose. You just know they will choose some direction or other. And that happens in lots of systems. It happens in ferromagnets. When a ferromagnet cools through the Curie point, it may magnetize in this direction or in that direction, and that choice is made spontaneously. It breaks the symmetry. There's a very interesting example, I think, which is liquid crystals. These are the simplest kind of liquid crystals, pneumatic liquid crystals. There is a high temperature phase in which they're made up of rod-shaped molecules, basically, and there's a high temperature phase in which they're pointing in any old direction, randomly. But when you cool through a transition temperature, you find a low temperature phase in which they line up. They like to line up parallel to one another. This is still a liquid. They can flow past one another quite easily, but it also has the feature of a crystal. It has an order. And in fact, many of you will have examples of this because liquid crystals are used in displays, because if you apply a little electric field, you can determine which direction they will take and change the system from being opaque to being transparent in a particular direction. Well, you've all heard about the Higgs particle, the Higgs mechanism, and this mechanism is very relevant to that too. Every kind of particle, as I'm sure you know, is associated with a wave. There's really no difference in quantum mechanics, in quantum theory, between particles and waves. Waves in the field are particles. For example, in electromagnetic waves, a wave in the field is composed of photons. You can think of a photon as a little clump of waves traveling along. Now, in most cases, the sort of normal average value of the field, the equilibrium value, if you like, is zero. The field just is zero, and you have oscillations about zero, which constitute the particles. But the Higgs field is a very unusual one. It has a different characteristic. It has two components, actually, or you can think of it as one complex field, if you like, H1 plus IH2, and it has a symmetric energy function. This is called the sombrero potential for obvious reasons. And this is just like the base of the wine bottle. It has a maximum at h equals 0 up here, and a minimum around the circle. So the natural thing for the Higgs field to do is not to have to be 0, but to have a value somewhere around here. And that's breaking a symmetry. In the vacuum, H sits somewhere down here, and it spontaneously breaks the symmetry, and that mass, that non-zero value actually gives mass to other particles. The way it does it is very similar to the well-known phenomenon of refraction. When a photon passes through a medium which contains free electrons, it's slowed down. Basically, the electrons have to participate in the movement of the photon. They're affected by the electromagnetic field. And so it effectively acquires a mass as it's going through the medium, and that goes slower. But notice that it doesn't lose any energy. This is not like going through treacle. There's no loss of energy involved. When the photon emerges from the far side, it has exactly the same energy that it had when it went in. It sort of lends its energy, if you like, temporarily to the electrons, and that slows it down, but it gets it back on the far side. And the same phenomenon occurs with the Higgs field. A uniform Higgs field is equivalent to a non-zero value, a non-zero value of the Higgs field is equivalent to a uniform C of Higgs particles. And that uniform C acts the same way as the free electrons in this refracting medium. So that's how the Higgs field works. Now, what was this for? Well, it has to do with unification. I'm sure you all know that many of the great advances in physics have been cases of unification. Newton unified our theories of falling apples and orbiting planets and the ebb and flow of the tides, which people had not realized were related to one another. He showed that they are. Clerk Maxwell unified in a similar way the theories of electricity and magnetism and light. Light is an electromagnetic wave. And Einstein unified space and time and gravity, showing that gravity can be understood as in terms of curvature of space. Now, where I come into this, where my generation of physicists come into this, starts in the period after the Second World War. So I want to tell you a little bit about Imperial College when I arrived, which was in fact in 1959. I have always thought that it was a piece of enormous good fortune that I was able to join the theoretical physics group here less than 3 years after it was founded by Abdus Salam. He was a really charismatic and enormously talented physicist. He already had a very strong international reputation by the time he came here. In fact, in 1959 also, he became the youngest fellow of the Royal Society at the age of 33. This was a wonderful place to do theoretical physics at that time. It was a really exciting group to join. There were lots and lots of visitors who came because of Salam's reputation. And he had a great interest in two things, symmetries of elementary particles, and unification, especially, as I will tell you, about weak and electromagnetic interactions. Let me remind you that we distinguish 4 classes of interactions. There are the two familiar long-range forces, electromagnetism and gravity, which are, of course, well known. And there's also the strong and weak nuclear forces, which are short range, and so not familiar to large-scale physics, because they're only relevant on the scale of the atomic nucleus or smaller. And all these are characterized by a coupling strength. For electromagnetism, this is the fine structure constant, which is determined by the charge on the electron and various other constants, and has a value of about 1 over 137. And there are corresponding numbers for the others, which at least in the 1950s were seen to be like that. And at that time, we had already got developed immediately after the war a really successful, a wonderful theory of electromagnetic interactions, quantum electrodynamics, which was brought to a mature form in the late 40s, and which describes electromagnetic interactions. For example, this is a scattering process. Conventionally, time goes upwards in these diagrams. It's a scattering of a muon and an electron, and that happens by the exchange of a photon, or more than one photon, but the simplest one is that. So we had this very successful theory of electromagnetic interactions, and this is a gauge theory. And what that means, you remember I mentioned the phase transformation of the wave function, but in quantum electrodynamics, it is possible to make such transformations in which the phase is a function of space and time. You can change the phase completely arbitrarily in space and time, provided that you make corresponding compensating changes to the electromagnetic potentials. And this is only possible if you have an electromagnetic field. And gauge theories have a lot of nice mathematical properties. So the next goal beyond that was to find equally good theories of the other interactions, or better still, of course, a unified theory of all of them, something we're still looking for. And it was suggested by many people that since this gauge property seemed to be produce a very nice kind of theory, they might be gauge theories with larger symmetries. And in particular, the weak interactions seemed to be promising because it was discovered that they could be understood as due to the exchange of a particle somewhat like a photon. This is another typical example of a weak interaction, a muon decaying into an electron and a pair of neutrinos. And that can be understood as due to, is mediated by this particle, the W minus. There are two of them, W plus and W minus, with two positive and negative charges. And so people started to ask the question, I think it was first asked by Julian Schwinger, could there possibly be a unified gauge theory with a symmetry of some kind between the W plus, the W minus, and the photon? And that would seem a very elegant extension of the idea of quantum electrodynamics to the weak interactions as well. But there was a problem. And the problem was that in order to understand the weakness and also the short range of the weak interactions, it was clear that the intermediate particles, the W minus and the W plus, had to be very heavy, something like 100 times the proton mass. But if you just put in by hand some mass terms into the theory, you got something which, that just spoiled the nice properties of gauge theories completely, and in fact gave you theories that were almost obviously inconsistent. So what to do? It was clear, I should say, that if there is a symmetry between these three, it clearly is a broken symmetry in some way or another, because they're not, the W plus and the W minus are massive, and the photon is not. So how could this be, how could this happen? Well, my introduction to this subject really was when a young US postdoc, Gerald Guralnik, arrived. He had actually already been working on this problem. He had been a student of Walter Gilbert in Harvard. And Walter Gilbert had in turn been a student of Salam's, so it was not surprising that Guralnik should come here. Gilbert, incidentally, was later a Nobel Prize winner for a completely different, medical work. Anyway, when Guralnik arrived, we started working on this problem. There had been a lot of discussion about the problem, of course, at Imperial before that. But we started working on it, and with another US postdoc, and we and others found the solution. And the solution is what is called the Higgs mechanism. There were three groups who independently came to essentially the same conclusion, starting, I may say, from quite different perspectives. Firstly, François Englert and Robert Brout from Brussels then Peter Higgs from Edinburgh, and then Veronica Higgin and myself here. All three of us published papers in Physical Review Letters, which is the physics journal, really. And Physical Review Letters selected these papers as among the most significant of 1964 when they did a sort of survey of these things. And in 2010, the 6 authors were awarded the American Physical Society's J.J. Sakurai Prize. These are 5 of us. Peter Higgs was unfortunately ill at the time, so he wasn't actually at the ceremony. And of course, it led further to a Nobel Prize in 2013 for François Englert and Peter Higgs. Robert Brout had died before that. Well, that is, of course, that is the Higgs mechanism. But how did this help with the unification? Well, actually, the unification requires a 4th gauge boson. It turns out, I don't know why Salam's picture has come up alone, but anyway. It requires a 4th gauge boson and a larger symmetry. It turns out that one needs W plus W minus Z0 and the photon to make it work. That modification is Glasser's particular contribution. And that had to be put together with the Higgs mechanism, which breaks the symmetry spontaneously. And being a spontaneous symmetry breaking, it doesn't spoil the nice properties of gauge theories. It gives masses to 3 of the gauge bosons and leaves the 4th one massless, the photon. And that does correspond to something like a phase transition in the very early history of the universe. The relevant temperature would be related to the mass of the W bosons and is around about 10 to the 16 Kelvin. And the expanding universe would have gone through that transition at 10 to the minus 12 seconds after the Big Bang. Well, that brings me, in a sense, to the end of that particular story. But I want to go on for the rest of the time to talk about a related phenomenon which has been of great interest to me over the last few decades. That is the problem of the phenomenon of defects. I said when you have a phase transition, the symmetry has to choose, the parameter, whatever it is, has to choose a direction in the relevant space. The direction of symmetry breaking, but it may vary from point to point. And if you have a large system like the universe, then you may well get completely different choices in different regions. And in that case, you may get trapped defects. For example, you can have grain boundaries in the crystal. The crystals may start to grow in different orientations at different bits of the system. A very interesting example is again in a liquid crystal. This is called a disclination. The defect is actually linear in this case. You have to think of it as coming out of the plane of the picture. And the point is that as you go around this, the direction of the molecules rotates by 180 degrees. If it was 360 degrees, then you could escape because they could all turn up in the middle. But if it's 180 degrees, they don't know whether to turn up or turn down. You can't escape from this. This is a topological defect. These are very interesting phenomena in their own right. They produce some really pretty pictures. If you take pictures in polarized light of liquid crystals, you can get things that show where all the defects show up. Very, very pretty and also useful. Now, in the mid-70s, I started to wonder, and others did too, whether you couldn't have similar phenomena for something like a Higgs field. The Higgs field doesn't have a direction in space, but it has a direction in this conceptual space with two components, H1, H2. And you could imagine a situation where if you go around a big loop, this direction rotates by 2 pi, 360 degrees. And if that happens, then it's clear that somewhere in the middle of that, it has to go through zero. What is happening is that the Higgs field is in the trough of the sombrero potential all the way around, but somewhere in the middle it has to climb over the hill. And that means there's extra trapped energy. There must be a line of trapped energy, which is what we call a cosmic string. And it appeared that cosmic strings might be formed at an early universe phase transition and could have very interesting cosmological effects. Actually, it turns out that this wouldn't work for the Higgs field itself, but there may be other Higgs-like fields associated with even higher energies for which it could work. Now, cosmologists became very interested in this phenomenon, and in the 80s particularly, and studied in considerable detail what sort of implications there might be, observational implications. One of the important things you have to do, of course, if you're going to make predictions, is you have to estimate how many of these defects will be formed, and then, of course, follow how they would evolve. But how many would be formed, it's not an obvious thing. But there is a causality argument that allows an estimate of abundance. But the problem was the argument was a bit rough and ready, if you like. And there's no way you can test the theory experimentally, because we can't go and do experiments on the early universe. And the laboratory experiments cannot get anywhere near the relevant energies. However, it turns out that a similar mathematical structure exists in many of the low temperature phase transitions. You can have tests in condensed matter systems. And I want to talk in particular about one, because I was involved in that particular one. The same mathematical framework can be used in condensed matter systems. And there, of course, you can go and do experiments and see exactly what happens. You can have a system and let it go through a phase transition at some rate and see how many defects you get. And one nice example is vortex formation in superfluid helium, helium-3 in particular. Helium-3 is a really wonderful material. It's an astonishing material about which whose symmetries are really remarkable. And it has a very rich family of defects, but included among those are vortices that are rather similar to cosmic strings mathematically. And such experiments were done. There were 2 lots of experiments done. This was way back now in 1996 in Grenoble and in Helsinki. One of the virtues of helium-3 is that it's a very good neutron absorber. You can have this reaction. A neutron is absorbed by a helium-3 nucleus and creates a proton and a triton, hydrogen-3 nucleus, and releases a fair amount of energy. And as this system cools through the critical temperature, vortices are formed. So the idea is you heat a small region up by firing a neutron in. It heats a little region up, it cools back through, and vortices are formed, and you observe them. I want to talk, the 2 experiments were very complementary, but I want to talk about the Helsinki one. This used a rotating cryostat. Rotation is very relevant here because superfluids have the remarkable property that a superfluid cannot rotate. Not if it doesn't have anything, if it's all superfluid. If you rotate the container, the superfluid will stay stationary. The only way it can rotate is if the vortices are formed, and you can rotate, you can have a flow around a vortex. But the flow in a superfluid is irrotational. That's the point. It has 0 curl. So it used a rotating cryostat and heated up a little region here. Vortices are formed, and then the vortices are captured by a force that applies to vortices, which is called the Magnus force, and they then migrate to join a central cluster. So there is a global rotation around the central cluster. The vorticity is concentrated in these vortices, and you can count them. It's a remarkable fact that you can use nuclear magnetic resonance to actually count those vortices. This is a picture of the nuclear magnetic resonance absorption over a period of hours, and each of these little bumps is one vortex joining the cluster. Well, in some cases 2, but so that's 33 vortices. So we could measure very, very well what happened. One of the reasons I'm showing you this is that I'm very proud of this one because it is the only paper, I believe, that is an experimental paper in physics on which I have had my name. I was not actually, of course, allowed to touch the apparatus, I should say. And you can have similar tests in lots of other theories. The key thing that we're testing here is a dependence of the number of defects formed, the rate of defect formation, on the rate at which the system goes through the transition, what's called the quench rate. Because if you go faster through, then there's less time for other parts of the system to learn about what direction has been chosen. You have to have causal interaction before you can, different regions can match up, as it were. So it has been widely tested in a lot of different systems. This has led really to some very interesting condensed matter physics. There's a new interest in rapid phase transitions. And the results on the whole have been encouraging. I should say this is, a lot of the theory of this is due to Wojtek Zurek. So it's sometimes called the Kibble-Zurek mechanism. There are some interesting exceptions, things that don't quite fit, but we understand some of those. Well, that brings me more or less to the end of what I want to say. I want to, before I finish, I want to express my debt to three people in particular. First of all, my father, Fred Kibble, who, as I told you, encouraged my interest in symmetries from a very early age, and I think influenced my career in that way. Abdus Salam, this is myself and Abdus Salam, in the early 70s, I believe. Salam was a really wonderful leader of our group and a very inspiring man. And then my colleague and long-term friend, Jerry Goralnik, who unhappily died earlier this year from a heart attack at the end of a lecture. Abdus Salam died, of course, in 1996. So I would like to finish with, this is a picture of me, as I said, in 1973 or thereabouts, but I should finish with a picture of Jerry and myself back in 1964 when we were doing this work. We were trying to emulate Einstein here. I've always thought that I won the battle of the tongues. Thank you.